Welcome to week 3 of the 2023 Amateur Radio Technician Class License Training. I hope you've all had a chance to review some of the material we've covered the past 2 weeks. So far, we've covered 4 of the 10 sections and that are covered in the test. First off, want to thank all of our partners, sponsors, whatever you want to call it, folks that have helped make this happen. 3 amateur radio organizations here in the county with a little bit different areas of expertise and interest. Our healthcare partners, Adventist Health, Public Health here in Mendocino County and Long Valley Health Center. Again, thank you all for helping make this possible. So these are the topics that are on the exam. Last week we did, Steve did radio wave propagation. I did a section on safety. Week before we covered some basic electrical principles and components. Tonight, first up, we're doing 3 segments. First up is signals and emissions. I'll be doing that. There's 4 questions on the test that come from the 48 in the pool. Steve will take over midway, or a third of the way through, I guess, with antennas and feedlines. And then I will finish up with practical circuits for the last segment tonight. So we'll be covering 10 of the 35 questions, material relating to 10 of the 35 questions on the exam. And here's some of the topics in the lesson that I'll be giving tonight. First is modulation. What that is actually adding information to radio signals. We'll talk about modulation techniques, the basic characteristics of common voice transmission modes. Also talk about a neat topic, and that is amateur satellite operations. Yes, hams have access to a number of satellites orbiting the Earth, and that's a fun topic to talk about. We'll cover the basic orbital concepts, some of the terminology, operating protocols, things of that nature. Also, the concept of telemetry, information that the satellite transmits. Touch on operating activities, and there's a wealth of them in amateur radio, all kinds of things you can do. The test focuses on just a couple. One involves radio direction finding. The other is contests and some of the information that goes along with contesting. We'll wrap up with non-voice and other digital communication methods. This is a very growing area in amateur radio. We'll talk about a little bit about image transmission and those other digital data modes. Before we go into that, however, let's take a quick review of some of the topics we've covered in the past 4 weeks. So we'll run through a few questions here, about 8 of them, to refresh your memory, let's say. So first question is, what is the term that describes the device's ability to amplify a signal? Is it the resistance, the forward voltage drop, the forward resistance, or the gain of that device? Well, if you have the ability to amplify a signal, that have gain. So gain is the answer to that one. What's the purpose of a fuse in an electrical circuit? Boy, you better know this one. Is it to prevent power supply ripple from damaging a circuit, to remove power in case of an overload, to limit the current to prevent shocks, or all of these are correct? Well, no, they're not all correct. A fuse is put into a circuit for one purpose, a sacrificial purpose, and that is to remove power in case of overload or excessive current. That's why you have a fuse or a circuit breaker in an electrical circuit, to remove power in the event of an overload. What's the formula to calculate voltage in a circuit using Ohm's law? Well, that is it the E, the voltage, equals the current minus the resistance? Is it E, the voltage, equals the current times the resistance? Or is it E, the voltage, equaling the current divided by the resistance? Or E, the voltage, equals the current I plus the resistance. Well, there's no plus or minus in Ohm's law. It's all multiplication and division. And the correct answer is E, the voltage in a circuit is equal to the current in amps times the resistance in ohms. What's equal to 1 microvolt? We did quite a bit on units and converting unit multipliers. A microvolt, that is 10 to the minus sixth. Well, the answer therefore would be 1/1,000,000th of a volt. A microvolt, 1/1,000,000th of a volt. Very, very small potential. Steve covered this topic last week. What mode is responsible for allowing over the horizon and VHF contacts over ranges of communication, to ranges of approximately 300 miles on a regular basis? Usually we think of UHF, VHF communications as line of sight. You can only transmit as far as you can see, but under the right conditions, you can go over 300 miles or more, and I know for sure more. And in the VHF, UHF range, which are not affected by the F2 layer or the D layer, the answer is tropospheric ducting. That's when a layer of stable air forms in the atmosphere, and the radio waves actually bounce back and forth off the top and bottom of that duct. How do you know when there might be a tropospheric duct occurring? Well, there are a lot of resources, including a map. You can get current data from websites that show you the likelihood of ducting events. It's not uncommon, especially in the summer, to have ducts form between the California coast and Hawaii. So sometimes you can talk to Hawaii on a handheld radio. Pretty neat. Oh, VHF, we mentioned that earlier. What are the frequency limits of the VHF spectrum? If you remember, there's rules of 3. We go 3 to 30, 30 to 300, 300 to 3,000 megahertz. Which one of those is the VHF spectrum? Well, the high frequency spectrum that is also known as shortwave operates up to 30 megahertz. If you move the next step up from high frequency to very high frequency, you are in the 30 to 300 megahertz range. So VHF 30 to 300. What is the name of an electrical wiring diagram that uses standard component signal? You want to sketch out what an electric circuit works like? Well, is it a printout, bill of materials, a flow chart? No. What you're doing is when you're sketching that out, you're making a schematic diagram of those components. It uses standard signals, and it shows how those components are interconnected. Nothing about their actual physical layout, just how wires or connectors or conductors go from the various components. Oh, this was a safety one, a very important safety one. Under what circumstances is it safe to climb a tower without a helper or observer? The person climbing a tower is at significant risk for personal injury, up to and including death. But is it okay when there's no electrical work being performed, or when there's no mechanical work, or if you're not more than 20 feet off the ground? You're just, you're only up 15 feet. Well, none of those are true. It's never safe to climb a tower without a helper or observer. Okay, let's move on to the first topic for tonight, and that's radio communications. Our universe is full, literally jammed full of electromagnetic energy at all wavelengths, including RF. Most of that is random electromagnetic energy. It comes from a variety of sources in the universe, and like I said, it covers a variety of frequencies and wavelengths. And for the most part, the energy simply exists. It's there. It doesn't carry information. It's what we typically refer to as noise. So what happened? How do we use radio waves to actually accomplish communication? Well, if we're going to use RF to communicate, there must be some way of adding and extracting information from that radio wave. So let's just look at the overall process during radio communications. First of all, from the transmitting end of things, the information that you want to convey, whether it's voice or data, video, commands, whatever, is converted to some kind of electronic form. The information in the electronic form then is added to a radio wave in a process that's known as modulation. The radio wave carrying that information then radiates from the transmitting station's antenna, goes out from there. Now the other side of the coin, receiving. The processes for receiving start with that radio wave that has radiated from the transmitting antenna being intercepted by the receiving antenna. The receiver then processes that, extracts the information from the received wave that was encoded into it or used to modulate the transmitting wave. And then the information is converted into a format that can be understood. It might be sound, it might be a picture, could be written words, could be a response to a command when you're sending a telecommand to a device, giving it electronic instructions what to do. So adding information to a radio wave. I mentioned that's a process called modulation. So adding information to a radio wave or a carrier is modulation. The very simplest form of modulation is to simply turn the radio wave on and off. And that's actually what's done in Morse code. A radio carrier is either allowed to be there present or not, and simply turning it off. Very, very basic form of modulation. It's also possible to encode sound or speech, music. Not on the ham bands, music is not allowed, but you can encode speech, sound, other things of the like. You can also encode or modulate a signal with digital data. And different modulation techniques alter different properties of a wave to add information. There's a couple of things you can do to a radio wave to modulate it, to encode that information that you want to transmit. One of the first is to modify the amplitude of that signal. We'll get into that in a second. Other ways are to alter the frequency or phase of the radio signal to add that information or to modulate. So what we're talking about really here are composite signals. The process of adding information to an unmodulated radio wave creates additional signals that are called sidebands. The sidebands in the carrier work together to carry the information. The combination of carrier and sidebands is what creates that composite signal, and we'll have a look at that here in just a bit. This brings up a concept of bandwidth. The carrier plus sidebands occupy a whole range of RF spectrum space. They're not just a discrete point in the spectrum. They actually sorry about that. They actually take up space in the spectrum. So the occupied range of that composite signal that's produced after modulation is known as the bandwidth of the signal. And as you can imagine, different types of modulation and information rates result in different signal bandwidths. And we'll look at some different modulation techniques and their associated bandwidths here. As we talked earlier, Morse code, very, very simple form of modulation. The signal's turned off, usually by using some kind of switch or a hand key. And you can see the graphic here depicts that as it's interrupted and it goes away. There's no signal. By turning the signal on again with the key to create Morse code characters, you're modulating that signal. Um, One of the earliest forms of voice communications was with amplitude modulation. And with AM, or amplitude modulation, the amplitude or the intensity of the carrier wave is modified in step with the waveform um, of the information signal. And you can see here that you have a modulating signal here that might be an audio tone, part of a voice signal. And if it's used to alternate the amplitude or the strength, the intensity of the carrier, you wind up with an AM signal, which is depicted in the bottom here. Oops, sorry about that. Let's get on to the next slide. So there are three components of an AM signal that we'll look at right here. There's the carrier signal. There are then the lower sideband depicted on the left on the screen here, and the upper sideband. All three of those are part of the composite signal, AM signal. So if you look at that, you might notice, you might not, that those sidebands are identical. They're mirror images of each other, actually, but they carry the same information. So really all the information that you need to extract the voice signal, excuse me, is contained in one of the sidebands, upper sideband, lower sideband. Either one contains the information. But that means that the AM signal bandwidth is twice that of the informational bandwidth. So let's look at something here to help visualize that. Here's an image of what's known as a spectrum analyzer. It looks at a range of frequencies and indicates the energy that's detected at those frequencies. Now, in this case, it's we're going to look at the bandwidth of an AM shortwave broadcast station. In this case, it's if you look here at the very bottom, it's the bandwidth of All India Radio. That's the shortwave station that's operating on a frequency of 7.550 megahertz or 7550 kilohertz. That's just above the amateur 40-meter band. Now you'll notice you can see the, right here in the center, you can see the energy from the carrier very plainly. And on either side of that are the sidebands, the lower sideband being below the carrier frequency, upper sideband being above the carrier frequency. You'll notice that those frequencies in this image range from about 7510 to, the overall, so the spectrum analysis is 7510 to 7580. The sidebands here are actually run from about 7545 to 7555. So this AM broadcast signal from All India Radio has a total bandwidth of about 10 kilohertz. It takes up some space in the spectrum. It means you can't have too many stations without overlapping. We're going to take a quick right turn here to non-voice modes just to get a comparison of bandwidths. As we mentioned, CW or Morse code, it's a very narrow bandwidth signal. It does not take up much real estate. The bandwidth of a Morse code signal, or CW, is approximately 150 hertz. Now remember that AM broadcast signal was 10 kilohertz, much, much wider. So hams are also authorized to transmit video, which is a non-voice mode, and using the AM mode of fast scan TV. What is that? Well, you're probably more familiar with it than you realize. It's a very wide bandwidth signal, almost 6 megahertz in total width. And it utilizes the NTSC protocol, which is the analog fast scan color TV, which was used for broadcast of TV signals until the last decade or so when digital television channels appeared. But Video, non-voice mode, AM fast scan, very wide, 6 megahertz wide signal, and it utilizes NTSC, which is voice analog fast scan color TV. So if you think about it, usable spectrum is really a valuable resource. You only got so much space between your band limits. So it makes sense to keep the working bandwidth as narrow as possible. This allows for more efficient use of the spectrum. Since the upper and lower sidebands contain duplicate information, why not transmit just one of the sidebands? And that's exactly what a mode called single sideband, or SSB, does. And in this, in the image here, it's depicting the upper sideband with the carrier removed or suppressed, and the lower sideband eliminated. This produces a much more efficient way of transmitting it, and you're able to recreate that missing character or carrier or insert it with circuitry in the receiver. So this results in a sideband signal that's approximately 3,000 hertz, 2,400 to 3,000 hertz wide for a voice signal. And that's half of an AM voice signal for amateur voice signals. So you can pack more signals in the same space. So single sideband modulation, where do you see it used? Well, it's used extensively on the amateur HF bands. It is indeed a form of amplitude modulation. It's not straight AM. You've kind of tweaked it a little bit, but it does use amplitude of the signal to modulate. It's a popular voice mode for long distance or weak signal VHF, UHF contacts. That's right out of one of the questions in the pool. Sideband, or as it's often called, is a voice mode for weak signal or long distance VHF, UHF communications. Again, approximate bandwidth, about 3 kilohertz for a voice signal, maybe a little less. And that's narrower than FM, which we'll explore here shortly. Typically, either sideband can be used. Either one can transmit the information you need. By convention, hams typically use or do use the upper sideband, the USB, on 10 meter HF, VHF, and UHF frequencies. That's also right out of the question. The upper sideband on 10 meter HF, VHF, and UHF frequencies. So let's jump to another concept and other methods of modulating a signal. First, let's review the concept of phase in an AC signal. It's an important property of the wave. The top graphic here depicts how the one cycle of an AC signal goes, starting at 0 degrees, will hit the voltage peak at 90 degrees, back to 0 at 180 degrees, will hit the minimum voltage at 270 degrees, and back at 360 degrees, you're back at 0 and ready to start the next cycle. So phases also can be used to define the position in a cycle. As I mentioned, at 90 degrees in a cycle, you're going to be at the voltage peak. Phase is also a way can be also used to express the relative position between two waves or their phase shift. In here, you can see a depiction in the center graphic of signals that have been phase shifted by 90 degrees, with the dotted line signal leading the other signal by 90 degrees. So frequency and phase may be modulated to encode that information into a radio signal. So if the information signal is used to vary the carrier's frequency, not the amplitude, FM or frequency modulation is the result. Voice bandwidth for FM is, depending on the design of the transceiver, between 5 and 15 kilohertz. 5 kilohertz would be a narrowband FM. The phase of a carrier signal can also be shifted in response to the information or modulating signal and creates phase modulation, which is depicted in the lower graphic. And really from a transmission and receiving standpoint, signal processing standpoint, phase modulation is very similar to FM, frequency modulation. So where do you find frequency or phase modulation used? Very, very commonplace on the UHF, VHF voice repeaters and on VHF packet radio, right out of the question pool. As I mentioned, for the approximate voice bandwidth, I'd said between 5 and 15, 10 and 15 kilohertz, somewhere in that range, certainly wider than the single sideband signal. One of the disadvantages versus single sideband is that only one FM signal can be received at a time. The way FM is detected and the audio pulled out, the strongest station captures the signal and takes out everybody else. So only one signal at a time with FM. Very, very commonly used VHF, UHF. This one's a little fuzzy, but if you squint, you can see it. This is just a recap of bandwidth, the typical bandwidths that you'll see with different kinds of signals. AM voice on the amateur band is going to be about 6 kilohertz wide. AM broadcast, about 10 kilohertz wide, as we saw in the spectrum analysis. Commercial broadcast video, which is the same as amateur fast scan TV, a whopping 6 megahertz wide. Your typical S sideband voice, 2 to 3 kilohertz. Down to CW at just 150 hertz. FM voice on amateur bands is quite a bit lower than the 150 kilohertz bandwidth that you'll see on an FM broadcast station. Okay, let's go through a few questions about the things we just talked about, see how much of that sunk in. So here's the questions of the pool. Which of the following types of signal has the narrowest bandwidth? Is it the FM voice, the sideband voice, CW, or slow scan television? Well, we didn't talk about slow scan. We talked about fast scan television. Well, we don't know anything about slow scan. We know FM voice is more than sideband. Sideband's a little more efficient, but the most efficient, the narrowest bandwidth of them all, is a CW, or Morse code transmission. Which sideband is normally used for 10-meter HF, VHF, UHF single sideband communication? Is it the upper sideband, the lower sideband, a suppressed sideband, or an inverted sideband? Well, we haven't talked about suppressed or inverted. I'm not sure they exist. We did talk about upper and lower, and either one will work, but on the 10-meter HF, VHF, and the UHF bands, you'll find hams using the upper sideband. And which of the following is a disadvantage of FM compared with single sideband? There's some pluses and minuses to both. No, the voice quality isn't poor. Actually, it's usually quite good on FM. They're not harder to tune, FM signals. So we know all these choices are correct. Is not the right answer. It only leaves one, and it's the one that we just discussed. And that's that only one FM signal can be received at a time. Okay, let's jump into something that's fun and, pardon the pun, truly out of this world. Amateur satellites. It wasn't too far into the 1960s that hams got the opportunity to communicate with each other using satellites, artificial satellites. This was, they were identified with an acronym called OSCAR. That stands for Orbiting Satellites Carrying Amateur Radio. And there's been a whole series of OSCARs. The OSCAR series of birds, as some hams refer to as satellites, are active today. They've been designed, built by hams. They are usually launched into space on the as a piggyback with other payloads going into orbit. These satellites, There's a variety of modulation modes that are used for satellites. All the common ones. You'll find some FM satellites, some that are analog satellites. They use sideband or CW. And you'll find others that utilize digital operating modes. So all of the common modes. Here's a satellite that you might not think of, but it is actually available for some amateur operations, and that's the International Space Station. There's a couple of ways that you can communicate or pass signals through the ISS. Another, to me, amazing aspect of amateur radio, that we have satellites and have actually had them for quite a while. And they're all designed and manufactured by hams. You'll find a lot of what are called microsats that are, say, designed and built by university engineering class and then launched into space. So, but if we're going to talk about satellites, there's some terminology that we need to cover. We'll run through these pretty quickly. The uplink, that is the transmission that a Earth station uses to send information to a satellite. Coming back the other way, downlink is a satellite transmission from the satellite back to stations on Earth. Satellites have beacon transmitters. And a beacon transmission is telemetry from a satellite, and it contains a status information regarding the satellite, maybe regarding its health or its status. And beacons send this information out on a regular basis. You don't have to be anybody special to receive it. Anybody with the right equipment, license or not, can receive satellite telemetry. This is an interesting concept, and you need to be aware of it. You hopefully are familiar with the Doppler effect. If you hear a siren or a horn or other audible sound coming at you, the pitch of that sound changes from that moving device as it approaches you and then as it passes you. You'll hear initially an upward and then a downward shift in frequency. The same thing happens on satellites. They're moving so fast that it actually produces a shift in the radio signal. And that observed change in the signal frequency is due to the relative motion between the satellite and the Earth station. So Doppler shift. As the satellite tracks overhead, the apparent frequency will start high and go to the center frequency and then go low as the satellite passes overhead. Most of the amateur satellites are in low Earth orbit, or LEO satellites. They're not way up there where geostationary satellites are. They orbit in a low Earth orbit, LEO. So some other terms that we need to know about when we talk about satellites. You need to understand that gyroscopic forces are needed to keep satellites from tumbling as they're in orbit. So satellites actually spin intentionally on their axis. This can result in spin fading, and that's caused by the rotation of the satellites and the antennas that it's using. So as the antenna satellites, you may hear the signal come up and drop and come up and drop, usually at a fairly low rate. Satellites don't spin that fast, but spin fading caused by the rotation of the satellites and the antenna. Something you got to know, and that is tracking software. If you are going to know, if you're going to operate through a satellite, you need to know when and where it will be in the sky above you and the path that it's taking. So hams use tracking software to get that information. These software programs use Keplerian elements. That's another old scientist, Johannes Kepler, which are elements used to describe the orbit of a body or around another body. And so the Keplerian elements are inputs that are used to provide orbital details calculated by the tracking software. That tracking software can provide real-time maps of the track of a satellite as it zips overhead. It can also provide or will provide the time the azimuth, the direction it is from relative to you, and the elevation at the start and the maximum at the starting altitude as it first becomes visible, the maximum altitude of the pass, and where it is at the end of the pass as it drops from view. So again, important information that you would need. You would get it from tracking software that uses Keplerian elements. Tracking software will generally calculate the apparent frequency adjusted for the Doppler shift. So you'll know where to tune your radio at the beginning part of the pass, where to shift it to at the mid pass, and where you'll wind up at the end of the pass. It's apparent frequency adjusted for the Doppler shift. There are one term that you need to know from the test question, and that is the mode that a satellite operates in. And it reflects the bands that the satellite is using for uplink and downlink. So a satellite that uses a 70 centimeter or a UHF uplink and uses a 2 meter downlink to send the information back to Earth, VHF mode, is operating in UV mode. So the first one indicates the uplink, the second one the downlink. So if it's UHF, VHF, as it is in this case, satellite's operating in UV mode. Okay, a few operating tips. Regardless of the mode that you're operating, you should use the minimum uplink transmit power. Why do you need to do that? Well, if you don't, your uplink signal that has excessive effective radiated power, ERP, the question states it as effective radiated power. Excessive uplink effective radiated power can block access to the satellite by other users. So if you're putting too much power, you're not allowing other users the benefit of the satellite. So how do you properly adjust your transmit power? Well, the recommended way to adjust the uplink power is to listen to your downlink signal from the satellite and adjust it so the downlink signal is about the same strength as the beacon signal coming from the satellite. It's the best way to know that you got the appropriate uplink transmit power dialed in. You monitor your downlink and try to adjust the transmit so the downlink signal equals the beacon signal. Okay, let's pop through a few more questions here before we move on to the tail end of tonight's or this segment. So quickly, what was a satellite beacon? It's the primary transmit antenna on the satellite, an indicator light that shows you where to point your antenna. Ooh, that'd be sweet. A reflective surface on the antenna? Maybe. But no, it's none of those. The beacon, satellite beacon, is a transmission from the satellite that contains status information or telemetry. It gives you information about maybe the health and status of the satellite. What is Doppler shift in reference to satellite communication? Is it a change in the satellite orbit, a mode where the satellite receives signal on one band and transmits on another? An observed change in signal frequency caused by the relative motion of the satellite and the Earth, or a special digital communication mode? Well, we just talked about that, and it's just like you standing on the corner when somebody honks their horn and drives by. There's a relative, that relative motion results in an observed change in the signal frequency, and that's because the satellite is moving so fast relative to the Earth that it shifts the frequency of the RF signal. And what is a LEO, L-E-O satellite? Is it a sun-synchronous satellite? Is it a highly elliptical orbit satellite? A satellite in low energy operation mode? Or a satellite in low Earth orbit? Ham satellites operate nearer to the Earth's surface, so most ham satellites are LEOs or a satellite in a low Earth orbit. Okay. While there are endless on-the-air operating activities, there's two that are mentioned in the technician test, so we'll go over those. First one involves radio direction finding, or RDF. Now, if you're going to do radio direction finding, guess what? You're going to need a directional antenna. That's something that Steve will talk about in the next section. But if you may use that directional antenna to do a couple of things. You might be able to use it to locate a source of interference, or in case of jamming, which is intentional interference, a directional antenna and RDF will help you locate that. Another thing that you might use that directional antenna for in an activity known as a hidden transmitter hunt. Those can be lots of fun, folks. Someone goes out and hides with a transmitter. They transmit periodically on and off, and then you use your directional antenna to try to locate that person in a competition that's often called a fox hunt. So operating activity using RDF, you'll need a directional antenna, maybe to locate interference or to hunt for a hidden transmitter. Contesting is the other activity that's mentioned in the test. Very popular. The goal of contesting is typically to contact as many stations as possible in a specified period of time. There's usually other constraints on that, frequencies, modes that define the bounds of a contest. But if you're operating in a contest, you want to contact as many stations as possible in the period of time allowed. So most people operating in a contest, they're not there to chat. They want to make a contact and then move on to the next contact. So good contest operating procedure is to provide the minimum information needed for the contact exchange. Again, that depends on contacts, but on the contest. But most VHF, UHF contests, you'll be exchanging your station call sign and your grid locator. And you'll keep it to a minimum as you're working the contest. You'll give the other station your location. You'll confirm that you received their location, and you move on to the next. That grid locator, what the hell is that? Well, it references a grid coordinate known as the Maidenhead grid system. And in the Maidenhead grid, every part of the world is divided into 1 degree latitude by 2 degree longitude rectangles. We call them often grid squares, but they're actually rectangles. So a Maidenhead grid is 1 degree by 2 degrees, and it's identified by a letter number combination. So typically 2 letters, 2 digits. And here in Mendocino County, most of the county is located in grid CM89 or Charlie Mike 89. So as I operate a VHF contest, I'll say this is WB9NJS, Charlie Mike 89, QRZ, and identify my location with that grid locator. What does that look like? Well, here's a grid map of the central to western United States. If you look closely, you can see California here. And right here is CM8 89, Charlie Mike 89. And yeah, that's pretty much most of Mendocino County. It starts down around Hopland, is the southern line, and then comes on up through the county. So that's a grid locator, often part of the exchange in a VHF UHF contest. Let's move on to digital communications. There are just numerous modes that use digital communication techniques to send sound, voice, or data. Using this technology that is developed and utilized by General Telecommunications, hams use voice over internet protocol, or VoIP, VoIP. Again, a lot of your phone systems these days utilize VoIP instead of an analog signal. So VoIP allows hams to deliver voice communications over the internet in a digital format. Why is that valuable? Well, there's a project out there called the Internet Radio Linking Project, or IRLP. What's this IRLP about? Well, it's used to connect amateur radio systems or stations or repeaters via the internet using VoIP. So you can actually connect the audio between two amateur stations using IRLP. This is pretty awesome. There are IRLP nodes all over the world, and it's quite often possible to connect your local IRLP repeater with other repeaters across the globe. And we do actually have some an IRLP repeater here in central Mendocino County. If you want to access different nodes through that, the way you do it is by sending commands with DTMF. The commands to access an IRLP node are sent using DTMF, which is also known as touch tone signals. And that's why many amateur microphones will have a keypad on the front. If you look at a microphone or a handheld radio, many of them will have a full keypad on the front. So Echolink is a unique internet-based system that allows you to transmit via a repeater without actually using a radio, using a computer as the interface instead. If you want to use Echolink, you have to register and make sure your call is registered and that they verify you have an amateur radio license, because at some point, although you're using a computer and VoIP, it goes out over radio waves. And in order to do that, it has to be under the control of a licensed ham. So you have to register and verify. So you may ask, how does all this amateur traffic get connected to the internet? Well, it's done by a gateway. Gateway is an amateur station that connects other amateur stations to the internet. Again, right out of the question pool. So, lots and lots and lots of digital modes. Some of the ones that are referenced in the question pool are packet radio, IEE 802.11, and FT8. Well, let's talk about some of those and what they really are. FT8, it's a digital mode that is capable of very low signal to noise conditions. What does that mean? That means it actually can function even though the signal that you're trying to use is barely above the noise level. Very popular mode, and again, you can actually make contact with signals that you can barely hear. Another one that's often used for EME, or Earth, Moon, Earth. Yes, hams actually bounce signals off the moon to talk to each other. Is a WSJTX. So you'll see that used for EME, Earth, moon bounce, weak signal beacons, or meteor scatter. Those are all modes where the signals are often quite weak. So WSJT, very commonly used in these very weak low signal to noise ratio conditions. Most of the modes, many of the digital modes use PSK, or phase shift keying, as the modulation technique. So PSK equals phase shift keying, right out of the question pool. Okay, we mentioned packet radio as one of the modes. Packet radio is used by the Automatic Packet Reporting System, also known as APRS. This is a neat system because through APRS, you can transmit GPS and mapping data, text messages, and weather information. Comes in really handy if you want a real-time image of, say, on a disaster response, where your resources are located. You could send that GPS information via APRS. Packet transmissions. One of the reasons that packet modes can be so effective is they incorporate different error correction techniques. What does that mean? Well, packet transmissions use checksums. It's a piece of information that's sent along with the packet of information saying, if you add everything up, there should be so many bits of data. So a checksum. They also, packet transmissions utilize headers that have the call sign and other destination information. And they also use an auto repeat request. So if the receiving station isn't sure that the accuracy of the transmission, it will automatically say, hey, send that again, send that packet again. This is an example of ARQ. It is an error correction or detection scheme where if the receiving station detects an error, it requests a retransmission of the data. Again, that's right out of the question pool. ARQ, receiving station detects an error. Hey, it says, hey, send me that again, will you? Okay. Getting down to the last tidbits here, which is good because I'm almost up to 7 o'clock. Digital mobile radio, DMR. What is that? Well, it's a voice mode that uses, from the question pool, time multiplexing. It uses time multiplexing to allow two digital voice signals to occupy a single 12.5 kilohertz repeater channel. Okay, so DMR, time multiplexing, lets you put two signals in the space of one. DMR repeater talk groups are used to allow users to share the channel without hearing the other users on the channel. Keyword there is DMR repeater talk group, and it's to share the channel without hearing others. Okay. One of the things I mentioned earlier as a digital mode was IEEE 802.11. 802.11 protocols, guess what? Those are your everyday Wi-Fi, internet Wi-Fi protocols, and you can use those to create an amateur radio mesh network. And those typically use commercially available Wi-Fi equipment that's operating with modified firmware in it. Okay, that's right out of the question. Commercial Wi-Fi with modified firmware. Well, the reason you can do this is the unlicensed Wi-Fi bands that your home Wi-Fi router uses actually has some overlap with amateur frequencies. So hams using that modified firmware can operate with higher power than normally available on, with your home router. They can do it legally by using amateur frequencies and create an amateur radio mesh network. So here we go. Last few questions. We're in the final home stretch here. What's a grid locator? Is it a letter number designator assigned to a geographic location? Is it a designator assigned to azimuth and elevation? Instrument for neutralizing a final amateur? Or is it an instrument for radio direction finding a satellite? Well, no, we talked about that. I showed you a cool little map. Grid locator is a letter number designator assigned to a geographic location. You give your grid locator, somebody knows approximately where you're located. How is over-the-air access to IRLP nodes accomplished? Well, you have to send some telecommands, and typically you do that by using DTMF signals. That's the touch tone pad on the microphone of your radio. So access IRLP modes, you have to know the right codes to use, but you enter the DTMF signal to control the IRLP node. And what kind of data can be transmitted by APRS, the automatic packet reporting system? GPS position data, yep. Text messages, yep, I said that. And weather data, yes, all of those are indeed correct.
We're on T9, antennas and feed lines tonight. And there are two questions on the pool. So my name is Steve Turner, and I'm up above Ore Springs on a ridge, and I've been a ham since 19 or 2008 this time, and I'm back in the 60s I was as well. So it's enough of that. So I'm doing a little different style than Tim does on the presentation. I'm going to basically give you the questions with the correct answer as statements in the slides that I'm presenting to you tonight. So we're going to start off with some vocabulary here. And the antenna system consists of the connectors, as you can see, that connect your radio to the feed line. The feed line then connects the radio to the antenna, and the antenna transforms that current that we talked about last week into radio waves when it's transmitting. And when the antenna is receiving those radio waves, the reverse happens. The current is generated within the antenna from the waves passing by the antenna. The current flows down the feed line through the connector into your radio. We will cover briefly some test and matching equipment because I believe we talked last week about how you need to make sure that the impedance of your coax matches the impedance of the antenna. And actually, we may not have talked about that, but it's important. It's a similar analogy would be you've got a 2-inch water line and you're connecting it to a 1/2-inch hose. You're going to have some resistance there that isn't going to help you move the water. In fact, if you had a pulsating water, it would actually create a backflow in that pipe. So we'll talk about matching your feed line and your antenna and your radio so that everything flows smoothly. So the feed line, as we said, carries the signal up to the antenna or the signal down from the antenna. There are several kinds of feed line. There are some examples here, the open wire and the twin lead. The twin lead on the top, many of you may have seen on the old television antennas when you were using antennas for your TVs instead of the internet or a satellite. The cable represented below that is called open wire line, and or window line, and you can see from the shape of it why it's called window line. The one on top is the twin lead is 300 ohms of impedance between the two leads. The open wire line is larger than is represented in this picture. It's actually about an inch and a half across, 1.25 inches across, and it has a 450 ohm impedance generally between the two conductors. That's kind of just information tonight. As you see in the green, what's really important for you to know is that 50 ohm coaxial cable, coax cable, is the most commonly used feed line in amateur radio. And coax cable, we will look at in the next slide, and I'll tell you actually how it's made. The lower illustration is the air-insulated hard line, which is the lowest loss. In other words, you're not losing the energy in the cable as you're trying to push it to the antenna. Loss is the opposite of gain. And we don't want to lose any of this energy we've created in our radio before it gets up to the antenna. It's especially important at the higher frequencies, VHF and UHF frequencies, because those signals get lost a lot faster in coax cable. The hard line uses air inside instead of the insulation that you see in the coax, which takes us to the next slide. A coax cable has a center conductor, a dielectric or insulator that prevents the signal from carrying to the braid, or in this case, a foil, which is a shield. This is considered a shield for the interconductor, but it's insulated by this dielectric from the interconductor. And then the entire package is covered with PVC jacket, a weather-resistant, sometimes underground-resistant jacket that protects the inside. I think it's been stated that you don't want to get water in your coax, because if you get water in between these layers, you get a very lossy signal. So again, 50 ohm coax is the most common feed line in amateur radio. The reason is, and these are all test questions, it is easy to use, requires few special installation considerations, and is not affected by nearby materials. I'm going to back up a little bit. Both of these twin lead and open wire line are what we call balanced feed lines. That's not on the test, but they're balanced because both of these conductors are above ground. They are not at ground potential. They are both hot. But if you get them near a metal object, like a downspout or a metal roof, it will distort the signals in this feed line and create problems in your transmission. Coax cable, because it has a shield around it, is prevented from having that effect when it comes past a metal object. So that's why it's easier to use coax, because it's not affected by nearby metal objects and so forth. However, coax cable, the loss increases with frequency. So you can use small diameter coax cable very efficiently at low frequencies, like the HF bands. Remember, the HF bands are between 3 and 30 megahertz. But the higher in frequency you go, the more signal this coax cable will lose in form of heat before it gets up to the antenna. The air-insulated hardline has the lowest loss at UHF and VHF frequencies, the high frequencies, really high frequencies. Remember, very high frequency and ultra high frequency. Because it's air insulated, it doesn't have this dielectric material kind of slowing down and dragging down the movement of the signal through the coax. And this is really coax. Coaxial means two axes, one inside the other. So this is your center conductor. The dielectric in this case is the air, and you have an outer shield. So the connector connects the back of your radio to this coax or this open or this air insulated hardline. And the PL259, it looks like this, the plug, the 259 plug, and the SO239, the socket, are the most commonly used on HF and VHF frequencies. Most commonly used. Above 400 megahertz, in other words, remember that 70 centimeter band we talked about last week, the first of our UHF bands, the N connectors are most suitable. The N connector here is designed differently and is lower loss. It's also more resistant to intrusion from water. As I said, coax connectors must be sealed against water when exposed to weather to avoid or prevent an increase in feed line loss. These are questions. These are questions with their positive, correct answer as a statement. Now, I want to point out a small thing here that's not on the test, but will be important to you. If you purchase a handheld radio after you get your license, an HT, a walkie-talkie, if you will, it will have a very small connector on it called an SMA. This is an SMA female, I believe, which is what you would use with a Bofang. An SMA male would look more like this. It would have a little protruding conductor in the center, and that would be more of a Kenwood style HT. But the thing that's really important is if you're using, at these higher frequencies, you want to use a large diameter coax or this air core dielectric coax cable. They're very rigid, much more rigid than small diameter coax. And so you see what we have here is a very small and lossy piece of coax. It's about a foot long, but it's flexible. And it connects to an SO239, equivalent of this, so that you can plug a regular PL239 with some big stout coax on it that will transport your signal at low loss up to your antenna without breaking the connector off the top of your radio. This is a stress relief item. Okay. And all coax connections must be sealed. So I mentioned that we have lossy coax. Our coax is lossy at higher frequencies. This is an example. And I believe that you've already been introduced to the term decibel. If you have not, a decibel is an indication of signal strength or signal loss. It's a measurement of the power in a signal. So one of the test questions is, what is the electrical difference between RG58, which is a small coax? This is the tiny one I showed you in that stress relief adapter cord just a second ago. It's very small, 174. But on the test, the question is, what's the difference between RG58 and RG13? Well, the answer is, the smaller the coax, the greater the loss. RG58 is much smaller. It's about 1/4 inch in diameter. 213 is larger than 1/2 inch. I believe it's about 5/8 inch in diameter. So because it's larger diameter and because also there's a little bit better quality in the shield in here, it loses less signal. So looking up above here, RG58 at 30 megahertz, remember, top of the HF band, is losing 2.5 decibels per 100 feet. That's almost half your signal, almost half the power. At 50 megahertz, the 6 meter band, it's almost twice that. At 100 megahertz, now look at the 2 meter band, which many of you will probably spend most time on, 6 decibels. That's 3/4 of your signal has been lost. 6 decibels in 100 feet. 3/4 of your signal gone if you use this. So you start out with 50 watts, you've got about 12 watts when you get to the antenna. However, if you're using 213, you see that it's still under 3 decibels, which means you've got a little more than half of your signal left. So your 50 watt radio is still producing maybe 28 watts up at the antenna after it gets through the 100 feet of this coax. You wouldn't want to use 100 feet of coax, but this is where how the tables are calculated. And you can see as you go even higher in signal frequency, the losses get greater and greater. Excuse me just a second. So these are some things that will are sources of feed line signal loss. Take a look at those and excuse me a second. We mentioned water intrusion a lot already. Multiple connectors in the feed line. In other words, you want to have, if you can, one length of coax between the connection on your radio and the connection on the antenna. If you have what they call barrel connectors, which are double females that connect cables together, every time you add something like that, you probably lose another dB or part of a dB, decibel. We just talked about what happens when the feed line gets too long. If you use the wrong feed line for the frequency, remember, you need to use the larger diameter feed line for the highest frequencies. The smaller diameter feed lines are more suitable for lower frequencies. High standing wave ratio is another way to lose your signal strength, but we have not talked about what a standing ratio is yet. So maybe we should. Remember I said if the so I told you that example of a large water pipe and a small hose creating some resistance there. Well, it's not a perfect analogy. So I'm going to see if I can stop this just where I want it, right about there, perhaps. Oh, what? Wrong one. Sorry. Maybe I can't freeze this. Okay. The green line that you see, the green wave that's moving to your right, is the RF power that you're transmitting to your antenna. And the blue is the energy that's being reflected back toward your transmitter because the impedance of the feed line is not a perfect match for the impedance that the antenna is exhibiting at the frequency that you are operating at. Now, antennas are tuned. They are tuned to a particular frequency, just like the pipe of an organ is tuned to a particular frequency. An organ might be a little bit more sensitive to being off frequency, and an antenna with some certain parameters can operate over a certain range of frequencies. But the farther you get from resonance, the impedance that it's presenting changes. It will either go lower or higher, and it will get other components that we won't need to talk about for this test called reactance. The reactance will change. So the red line is the sum of those two waves. So let's see, how can I illustrate? So you notice here when the two peaks merge, right here, the red wave is the highest because the voltage on the coax cable is a combination. It's a sum of the energy being sent out by the radio and the energy being reflected back by the antenna. So this voltage is higher. It's the sum of the two. That voltage can damage your radio. Thus, if you have a high standing wave ratio, the voltage and the current in the feed line can actually damage the transmitter in the radio. So most of your radios are designed these days to start reducing their own power if they feel this high standing wave ratio coming back at them, this energy. They'll measure this voltage and say, oh, that's too high. I need to start backing off on this green voltage so I don't I don't burn out my transmitter. So like I said, this is a test question in the form of a statement. The standing wave ratio is a measure of how well a load, in this case the antenna, is matched to the transmitter coax, the line. As I said, the high SWR causes signal loss. And here's a couple of examples. 1-to-1 is a perfect match where your 50 ohm coax and meets your antenna, and the antenna is tuned properly and it's matched and it's presenting a 50 ohm load. No power bounces back to the transmitter. It all is presented on the elements of the antenna and radiated. 1.5-to-1, you're losing 4% of your power. Greater than 2-to-1 is more than 11% loss, and this is where the equipment will start to dial back their power. So if you start losing more than 11% of your power, they'll actually reduce power. Now you're losing even more because you're only maybe putting out half the power that you started with, and you're still losing more than 11% on top of that. 3-to-1 SWR is a quarter of your power. So not only can you lose power in a coax that's too long, or a coax that's wet, or a coax that has loose connections, or a coax that has too many connectors in it, you can lose power if you have a mismatch between your antenna and your coax. So a device has been invented here, and it is called an antenna tuner or an antenna coupler. And as it says here, the major function of an antenna tuner or coupler is to match the antenna system impedance to the transceiver's output impedance. Now, this blue line represents the transmission line, the coax, from the antenna to the tuning unit. The tuning unit is then connected with a short piece of coax to the back of your radio. I'm going to make a technical distinction here. This antenna tuning unit is matching the coax and the load that the combination of the coax and antenna are presenting to the radio. They're matching that so the radio won't dial back its power. It's really tuning the combination of the coax and the antenna. So if you have a high standing wave ratio, this antenna tuning unit will match the coax to the radio, reducing the standing wave ratio at the radio, but it will not reduce the amount of energy you've lost in your coax. To do that, you'd have to put this antenna tuning unit at the antenna, which is more difficult because as you change frequency, you have to adjust the components in the antenna tuning unit. This is more relevant at HF frequencies for us than it is at VHF and UHF frequencies. So this would relate more to your 10-meter band privileges and the privileges that you have on CW on 80, 40, and 15 meters. Okay. A little more vocabulary, excuse me a second. So the element is the conducting part of the antenna that actually radiates the radio signals or receives the radio waves. And I got a couple of examples back here, but they're not really good. So let's show you this. Well, you can't see this because I'm not sharing my screen. I'll show you that later. So the feed point is on the antenna where the transmitting energy enters the antenna. The radiation pattern is the direction of strongest radiation and reception. We talked last week about omnidirectional antennas and directional antennas. I think we did, and we're going to talk about that again in more detail. But we did talk about the pattern of radiation coming off of an antenna. So this example is a half wavelength antenna. A half wavelength antenna will have the voltage. The wave will actually rise on one side. The voltage will be at 0 as it crosses the center of the half wavelength. Oops, I'm sorry, that would be full wavelength. I'm wrong. The voltage will be highest at the end. It will gradually decline. It will be lowest at the center. And then it will go into negative and be the most negative voltage on the other side. It's only half of the wavelength. It doesn't come back up. You see, it's half wavelength long, but this is pretty much a perfect antenna, a half wavelength antenna. And because it's a half wavelength antenna, the current is the highest in the center. And that allows us to use a 50 ohm coax, a low impedance coax. And it's also perfect because the current in the antenna is what radiates the energy. And the current is highest in the center because the current the current curve is highest in the center and lowest at the ends because the current, remember, the current is 90 degrees from the electrical, or the magnetic field is 90 degrees out of phase with the electrical. We talked about that. And 90 degrees that Tim just talked about is that 90 degrees. So that when the voltage is high, the current is low. When the current is high, the voltage is low. Ohm's law. Okay. Now we're going to get back to the question statements. So, a half-wave dipole radiates the strongest signal broadside to the antenna. What's broadside? Broadside is this, right? It's not off the ends. Off the ends is not the strongest. It is broadside. So if you are looking at the diagram we just had, and the wire that we shown was right through here. This is the antenna driven element right here, the antenna element. The signal, if you were looking straight down from above, is strongest broadside, and these are decibel measurements. And as you get further off of this 90-degree broadside, the signal gets a little weaker and a little weaker and a little weaker. And at the ends, there's almost no signal coming out this side. You see, this is the direction the signal is traveling in here. Broadside to the antenna and very weak off the ends. If you didn't have ground under it and it was like in the middle of space, this radiation pattern would look like this donut, because there'd be nothing under it to absorb the energy like this antenna will be on the ground. If it's close to the ground will absorb this bottom half of the donut. But you will still have energy going up at certain angles. This is the takeoff angle that Brett asked about last week. What is the angle of radiation? The angle that the radiation is taking off at from this antenna. If it takes off on the horizon, like we talked about for VHF and UHF, it'll go farther. If it takes off at a high angle at UHF and VHF, it'll go right through the ionosphere and out into space. You'll never hear it again. So this is the angle of radiation that's represented here. Remember, this is the question, and the rest of this is giving you some background. So our graphic here is showing you that the strongest signals are broadside to the element. Now, you need to know the formula for calculating this half-wave dipole. And I wish we would start off, actually I'm going to start off with the next slide first. Yes, because this is easier to remember. 2, 3, 4. How many of you can remember 2, 3, 4? If you take 2, 3, 4 and you divide it by the frequency, you will find that a quarter wave element, a quarter of a wavelength, is 1.6 feet. Multiply that times 12 inches, you get 19 inches. Now let's go back. This example is on the test, but it's a half wave. A 6-meter dipole is a half wave. A dipole, two poles. The left side and the right side. So it's doubled, 4, 6, 8. So 2, 3, 4 gives you a quarter wave. 4, 6, 8 gives you a half wave. I think it's easier to remember this. 2, 3, 4 is easy to remember. You just double it. 4, 6, 8. Divide by the frequency, you get the number of feet in the half wavelength. Now, multiply times 12 inches, and a half wavelength antenna, like the one we used in our example, would be 112 inches, 112.3 inches long. These in the greens are questions, right? And this is actually one of the questions. How many inches long is its dipole? One of these figures will be asked. Shortening a dipole will increase its resonant frequency. Remember, the wavelength gets shorter the higher the frequency. Back to our example of waves. The longer the wave, the lower the frequency. In other words, the longer the wave, the lower frequencies travel farther before they complete the complete wave. Higher frequencies mean that they're completing their waves really fast, and over that 1 second interval, it's a higher frequency, and so there's more waves, short waves packed into that frequency. And a simple dipole oriented parallel to the Earth's surface is horizontally polarized. This dipole, if this is parallel to the Earth, it's horizontally polarized. It's polarized to send its signals to the horizon. That's the electrical, remember, that's the electrical charge on the antenna. That's the one we use to illustrate the polarity of the antenna. Okay, now on to the quarter wave, which we already looked at, 2, 3, 4. Now some details about antennas here. Remember we talked about this antenna is resonant at exactly one frequency. However, if you make the rods thicker, the diameter of this element thicker, you can broaden the resonance a little bit and make it resonant over a little bit wider range of frequencies. You see that the impedance of a quarter wave antenna is between 35 and 50 ohms. 50 is what our Feedline impedance is. So we really need to try to stay as close to 50 ohms as we can. In this case, the angle of these radials can influence the impedance of this driven element, this radiator. Let's see. Okay, sorry about that. We haven't talked about the half wave. The half wave dipole is between 50 and 70 ohms of impedance. It varies depending on how high above the Earth it is. And so that's why 50 ohms has been chosen by most manufacturers to manufacture their radios to match as close as they can to 50 ohms. And that's why we tend to use coax, which is 50 ohms impedance, to try to make all these things work together. Now, remember the dipole has two halves. A quarter wave antenna is only one side of that dipole. We have to have something, radials above ground like this, that you can see, or buried in the ground underneath the element, the driven element, which is what you probably would do with high frequencies like 10 meters or 40 meters or 80 meters that you have privileges in, because they become pretty long. This is 19 inches at 2 meters, but at 40 meters, this is 33 feet. And so the radials would need to be 33 feet if they were in the air like this. If you can put them underground, you have a little bit more flexibility of how long they are. They don't have to be resonant, but this driven element does. Now, so you see here, half the dipole must be present either as radials, a reflective surface like the top of your car, or a capacitive connection to the Earth. And the body of your car actually makes that capacitive connection to the Earth for you. So the metal surface and its relationship to the Earth forms the other half of a dipole. When you're using a handheld radio, your body forms the other half of the dipole. You are making a capacitive connection to the ground. And that's why you generally can't get more than about 5 or 10 watts in a handheld radio, because you're now carrying that signal through your body. Now, directionality. A quarter wave antenna that's vertically polarized is omnidirectional. In other words, this little Volkswagen here is going to be radiating energy broadside off this vertically polarized antenna. And so the energy is going to go straight out at the horizon. This is really good for VHF and UHF because you have direct line of sight propagation, remember, most of the time. Also, you want that really low angle of radiation. You don't want the antenna radiating off like this, because if you're looking for that tropospheric ducting that Tim mentioned that we talked about last week, this low angle will generally be better for you because it'll duct around the Earth with that air mass rather than going off into space. Remember that we can't cross polarized antennas, especially at the higher frequencies, UHF and VHF. The receiving and the transmitting antennas must match. Otherwise, you'll lose about 20 decibels. And remember, 20 decibels is, if you start with 100 watts, you end up with 1 watt, 20 decibel loss. Okay. However, there's an exception. We talked about this last week, I believe, for elliptically polarized waves, such as the ones you get reflected back from the ionosphere. You don't have a choice. I mean, they're being polarized by the ionosphere, and so you take what you can get, and it doesn't matter whether your antenna is vertically or horizontally polarized. So, antenna gain. If you can lengthen a quarter wave antenna, and we're talking UHF and VHF here, that quarter wave ground plane antenna with those 4 little radials to a 5/8 wave antenna, it aims more energy. It aims more energy down. So this is the radiation curve of that quarter wave antenna. It kind of looks like a dipole, doesn't it? Because remember we had the dipole donut radiating broadside, but since we've got the ground here, we've only got half the antenna. We only get the above the horizon part. So most of the energy is going straight out. Well, actually, it's kind of divided up, right? It goes, some of it goes this way and out here and out here. If you go to a 5/8 wave antenna, it concentrates a lot of energy at a lower angle. 3 dB, it says here, 3 decibels. That's doubling your effective radiated power at the horizon. You see it. There's some phasing things and all kinds of magic going on with that antenna. So there is still some radiation up a little higher. But you see, this part of the quarter wave antenna has been concentrated into this lobe down here, this lobe. So by inserting an inductor into the base of this antenna, it makes it longer electrically. This is referred to as antenna loading. It's not the only time we use antenna loading, but that's how you can make an antenna longer without physically making it longer. A beam antenna, and I'll show you examples of both these here in a minute if we have time. A beam antenna concentrates signals in one direction. Now, the way it does that is by putting additional elements in next to the element that you're energizing, that you're driving. So if this is the dipole, this axis here is your dipole, instead of radiating here and here, by putting an element behind it, a little bit longer, a little bit lower frequency, and another element in front of it, come on, get back, a little shorter a little higher frequency element, it tends to concentrate the signal in that forward direction, while the element in the back that's lower frequency tends to reflect that forward. So this back element then would be called reflector. The element that's being energized is a driven element. It's being driven by the transmitter. And there's a directing element or more in front. Sometimes you might have many directors in front, usually only one reflector in the back. So the more directors you put in the front, the more focused, the narrower the signal pattern becomes, but the more concentrated the signal gets, and so the more energy you get. You're not adding power, you're simply concentrating it in the direction you want it to go. There are methods to do this with vertically polarized omnidirectional antennas too, where they stack elements one on top of the other and make the pole taller. So a couple of quick vocabulary things. An isotropic antenna radiates equally in all directions. It's really a point in space, if you can imagine something like that. Gain is increasing that signal strength. It's just like an amplifier, except in this case, it's focusing the energy. Omnidirectional, like I said, refers to all directions around. Directional beam, test question, concentrates energy in a specific direction. Here are examples of those antennas. The isotropic, the 5/8 wave vertical has that lower concentration of energy compared to what that more donut-shaped quarter wave. And this J-pole you will become familiar with because many hams around here use J-poles. This is actually a half-wave antenna with a quarter wave matching antenna below it. Gives you kind of a funny pattern. And the Yagi that we had in our last slide, this is the driven element, this is a reflector, and these are the directing elements here. See the feed line coming off of the driven element. I realize we're just about running out of time here. So, one more thing. You have to have an antenna that's at least a quarter wavelength long. If you don't, your antenna is going to dissipate a lot of the energy in the form of heat. This rubber duck antenna, this short antenna that you'll get on top of a handheld that you buy, is just a coil of wire. It resonates, but most of the energy turns into heat. So you can buy longer antennas for the Bofang or whatever handheld you want and get more efficiency. My suggestion would be that if you are going to use any kind of a mobile setup, that you get a magnetic mount. This is the beginning anyway. Later on, you can get more professional looking, but this magnetic mount works fine. Put the antenna on that. You can take this antenna off and you can put it on a ladder in your backyard, or you can put it on the patio on a pizza pan to give it that reflective surface below it. And you can connect it with that flexible connecting I told you to the top of your handheld. And then you've got the efficiency of the bigger antenna and the flexibility of moving around with it with your handheld. Now, does not transmit or right. This isn't as efficient, doesn't work as well. You can't use it inside a vehicle because it will, the vehicle will capture some of the energy. These are test questions, test answers.
We're on the final segment tonight, T7, Practical Circuits. You will find, as is typical in the question pool, there is often overlap between various sections. So I'll be talking about some things that Steve just talked about, but the questions appear in both segments of the question pools. Okay, topics in this lesson: basic test equipment. We'll talk about using Voltmeter, ammeter, ohmmeter are often combined into a multimeter. The station equipment and some terms about transmitters, receivers, transceivers, amplifiers, hardware of that sort. Some of the characteristics of a receiver that you want or a transmitter. Talk briefly about some very common circuits that you'll find in most radio equipment. Common problems and solutions, that's both transmit and receive. You have on-the-air problems. Sometimes those problems include interference, which is seldom a good thing. And tying in with Steve's presentation, talk briefly about antenna and transmission line measurements. And that includes SWR measurement. As Steve mentioned, that standing wave ratio is an important thing. And overlap on some of the feed line characteristics and failure modes. Common measuring tools, a multimeter. That is a meter that can measure multiple quantities. You'll see what that looks like here in a second. A standing wave ratio meter, SWR meter or bridge. Antenna analyzers are also a way to check impedance match. And a directional watt meter is another way to assess your match and your standing wave ratio. Multimeters, they're pretty common. The old style is what you see on the left, an analog, a mechanical meter. Most of them today are digital meters. You can measure all components of Ohm's law with a meter, an appropriate meter. Multimeter or volt ohm meter sometimes, it can measure volt, ohms, amps. Voltmeter measures electrical potential. I believe that's the way it's worded in the question, which is voltage, and it's measured in parallel with the circuit. An ammeter measures current, that's measured in series with the circuit. An ohm meter should be used generally only on de-energized circuits. You don't want to be using an ohm, trying to measure resistance in an active circuit. So recapping what I just said, the voltmeter, if you remember from the schematic symbol, it's a circle with a V in it. It's been connected here in parallel with a battery to measure the voltage across that battery. An ammeter has been connected in series with whatever component this is. It could be a light, it could be some kind of load. And the ammeter there is in series, the voltmeter is in parallel. When you use a multimeter, there are things you need to be careful about. This is again overlap we talked about last week. If you're measuring high voltage, you need to be careful. Make sure the meter leads and the meter are rated for the voltage you're trying to measure. Take care to ensure the operator running that meter does not contact the high voltage in the circuit. As I mentioned, you do not want to try to measure ohms or resistance in a powered circuit. Doing so is likely to damage the meter circuitry. That's out of the question pool. You may connect an ohm meter to an unpowered circuit. It's sometimes difficult to get an accurate reading, but if you connect it to an unpowered circuit and the resistance reading increases, indicates increasing resistance over time, that's an indication that the circuit likely contains a large discharged capacitor. That's the question. Okay, shifting gears real quick. Electrical connections are usually made, solder is a technique used to make electrical and mechanical connections. Solder is a low melting point alloy, traditionally lead tin alloy, now often a copper or tin and copper alloy. Shift away from the lead to reduce the toxicity concerns, exposure, but it's a low melting point alloy. When you're using solder for electronics, you want to make sure you are using a rosin core solder. That's intended for electrical work. That rosin core in the solder helps the molten solder flow onto the metal surfaces. You do not want to use acid core solder. Acid core solder is intended for plumbing. That is not something you want to use with electronics. You want to use rosin core only. There's a bit of technique involved in soldering. You have to apply enough heat to these surfaces being joined. If you have inadequate heat, a cold solder joint can result. You can usually pick them out because they tend to have a rough, lumpy surface or kind of a dull look to them. A good solder joint is bright and shiny. Problems with cold solder joints is they can cause an intermittent connection, which is sometimes a headache to troubleshoot. Okay, standing wave ratio. Steve mentioned just a few minutes ago. It's a measure of how well a load is matched to a transmission line. From the question pool, a reading of 1-to-1 indicates a perfect impedance match. A high SWR, 4-to-1, indicates impedance mismatch. Again, taken right from the questions. When you do have a high SWR, as Steve mentioned, the energy is reflected from the antenna back to the transmitter, and that can cause problems. So protection circuits, as Steve mentioned, are often designed into solid-state transmitters that will automatically reduce the power when that standing wave ratio increases above a certain point. And the intent there is to prevent damage to the output amplifier transistors in the transceiver. Again, right out of the question pool. Standing wave ratio meter or bridge. When you use it, it's inserted in the feed line between the transmitter and the antenna. An antenna analyzer is another way to determine impedance match. It's often a little more expensive than an SWR meter, gives you additional information. Directional watt meter is another device that may be used to determine SWR. Directional watt meter can measure forward versus reflected power, and comparing those gives you an indication of the standing wave ratio. This is what an SWR meter looks like, a standing wave ratio meter. You'll notice it says SWR and power meter. It's for 140 to 525 megahertz. A series of switches here. You'll notice this power switch can go between forward and reflected, so this is a directional watt meter. It also has a capability of being put into a position where you can measure standing wave ratio, and it operates on a multiple range of power settings. Antenna analyzers look something like this. Again, they can give you a lot more information about impedance mismatches, including the actual measurement of impedance. You can use that on an antenna. You don't need a transmitter. For an SWR meter to work, you need to have a power source to measure what's been forward and reflected. Antenna analyzers have that built in, and you can hook them directly to the antenna for measurements. High standing wave ratio may be due to coaxial feed line failure. Steve touched on this. It's in this section as well. That moisture contamination in a coaxial feed line is one of the most common failure modes. That's why the outer jacket of the cable, it's a water barrier, so it must be resistant to ultraviolet light. If it's not, that jacket can break down and allow water into the cable, which is a bad thing. And the air core coaxial cables that Steve showed, where there's very little material separating the inner conductor from the outer conductor or shield, they require special installation techniques to make sure that water does not get in. If it does, that air core coaxial cable can act just like a pipe, and you can have water running out at the bottom of your tower. So real quickly, how is a voltmeter connected to a component? If you're going to measure the applied voltage, voltmeters are connected in parallel, as I showed in the diagram. Which of the following can damage a multimeter? You don't have to let it warm up, not these days. The biggest problem comes around if you're attempting to measure voltage when it's in the resistance setting. Voltage would be present in a powered circuit. If you're trying to measure that with the resistance setting, you may damage the meter. What does an SWR reading of 4-to-1 indicate? 4 dB loss, good impedance match, a gain of 4 dB, or an impedance mismatch. You don't want to see 4-to-1. That's a sign of an impedance mismatch. Which instrument is used to measure electrical current? Well, current is measured in amps. So an ammeter is used to measure electric current, and it's in series with the circuit. Which instrument can be used to determine SWR? Voltmeter, ohmmeter, they're not sufficiently sophisticated. Iambic pentameter has nothing to do with radio. The answer is a directional watt meter, like the little one I showed you in the picture. So what's amateur station with the very basic equipment? Well, you're going to need a receiver to detect signals, radio signals. You need a transmitter to generate radio signals. Most often those functions are built into a single unit that's known as a transceiver. So most of the time these days, because there's so many common parts of the circuitry, everything's bundled into one box, and your transmitter and receiver are rolled into a transceiver. Couple important things for a receiver to do. One is, and it comes down to hearing a signal and just one signal. Sensitivity, this is a term in the test. Sensitivity is the ability to detect the presence of a signal. So the sensitivity of a receiver is its ability to tell if there's a signal there for it to detect it. Selectivity is the ability to discriminate between multiple signals. If you've got a lot of signals and you only want to hear one, you want a receiver with good selectivity. A lot of basic electrical circuits are found in transceivers. One is an oscillator. Oscillators generate a signal at a specific frequency. That's right out of the questions. A mixer. Mixers are very common, and mixers are used to convert radio signals from one frequency to another. So you'll find a mixer in your transceiver, many of them. Modulator. Oh, well, you need that modulator circuit because it's the process of combining speech with the RF carrier signal. That's part of the question. Modulation is the process of combining speech with an RF carrier. PTT, that abbreviation stands for push to talk. What is push to talk? That's a switch or a button, usually on the side of the microphone, that switches the transceiver between receive and transmit modes. And I believe in the question it says when grounded. But the PTT line, when grounded, will switch the transceiver between receive and transmit mode. Push to talk, you need to turn the transmitter on. Amplifier circuits. Steve mentioned power gain and power loss. Amplifier circuits are used to increase the power level of a signal. They work both ways. You can use an RF preamplifier. RF preamplifier is installed between the antenna and the receiver. Its job is to boost the incoming signal. It effectively increases the sensitivity of the receiver by providing more signal to work with, although at very low power levels. So receivers don't need a lot of input power. The other kind of amplifier that's in the test is an RF power amplifier. What do? Well, they may be used to increase a low power output, say from a handheld transceiver up to from, say, just a few watts to several watts, maybe even 100 watts. But RF power amplifier. Quite often on them, you will find a single sideband or CWFM switch. And the reason that switch is there is to set the amplifier for the proper operation in a selected mode. An amplifier operates differently for single sideband than it does for CW or FM. So there needs to be a switch to set the proper operation. Again, right out of the questions. A special device is known as a transverter. It's a transceiving converter. Transverter, what does that do? Converts the RF input or output of a transceiver to another band. Well, this can be handy. As we mentioned, mixer circuits can allow you to shift frequencies. It utilizes mixers to convert those frequencies, both transmit and receive. And it's a very cost-effective way to be able to operate on another band. You can use a 10-meter transceiver or a 2-meter transceiver, 144 megahertz, As you run that through a 10 gigahertz transverter, now you can operate on the 10 gigahertz microwave band using a transceiving converter or a transverter. What's a transceiver? Is it matching? Is it combines the functions? Well, that's an easy one. That's a no-brainer. Transceiver combines the function of a receiver and transmitter. Name of a circuit that generates a signal at a specific frequency. Well, that little devil is known as an oscillator. Which term describes the ability of a receiver to discriminate between multiple signals? Well, first thing is to hear them, but you got to be able to distinguish between them. That term is known as the selectivity of a receiver. Which device converts RF input and output of a transceiver to another band? Well, that very handy device is known as a transverter. If you're going to use an RF preamplifier, where do you install it? Well, it is best installed and only functions effectively between the antenna and the receiver. That's where you install the RF preamplifier. When you're on the air, you may get some reports that there's problem with your signal, and those on-air reports, if you know how to interpret them, can help you to identify the problem. If you're told that you're over deviating or that your signal will be, particularly into a repeater, may sound distorted or it breaks up, cuts in and out because of over deviation. If that's happening, it's the simple solution, if you're told of over deviation, is to simply back off from the microphone. Don't speak so loudly. If the more in FM, the more audio you put into the microphone, the more deviation it creates in the frequency. So if you're over deviating, back off. Sometimes you'll get a signal report. Is your signal's been reported as garbled or distorted or unintelligible. It just doesn't sound right. That's often a symptom of RF feedback in the transmitter or the transceiver. Some of the RF energy that's supposed to be going out to the antenna is somehow getting mixed back into the transmitter itself, creating RF feedback, garbling and distorting the signal. You might be told that your audio through a repeater is distorted or unintelligible. Several things that cause that. Could be that your transmitter's slightly off frequency, you bumped the knob, you're not quite where you thought you were. Batteries, especially in a handhold, might be running low, or you're simply in a poor location. All of those could be causes for a report of a distorted, unintelligible signal through a repeater. Well, interference. That is a common problem for hams. It's a problem whether it's generated or received by your station. One way to minimize interference, unnecessary interference on the ham bands, is to use a dummy load or a dummy antenna when making transmitter adjustments. What's a dummy load? It's a non-inductive resistor with a heatsink. It takes place of the antenna, and it prevents the signal from actually going out over the air. The non-inductive resistor will dissipate the power from the transmitter, turns it into heat. This is why you need a heat sink. So yeah, use a dummy load if you need to make adjustments with your transmitter so you're not transmitting over the air. Radio frequency interference and television interference, excuse me, RFI and TVI, headaches for all involved. It's generated by your station operation. It is a problem for you and your neighbors. Three very common sources for RFI or TVI, and these are all of the above in the question. One is harmonic radiation, one is spurious emissions, and the other is fundamental overload. Okay, we won't go into what all those are because we're a little short on time, but it is in the notes. So fundamental overload, that's when the receiver is just swamped. It can't handle all the energy that's coming into it. And that can cause an AM or FM broadcast radio to unintentionally receive a ham signal by fundamental overload. The overloaded receiver is just unable to reject those strong out-of-band signals. You can cure this by installing a filter at the antenna of the affected receiver radio to block the ham signal. Your VHF transceiver may be overloaded by a nearby FM broadcast station. Now, you're having a hard time hearing because of all this excessive energy in fundamental overload. How do you fix that? It's possible to install a band reject filter on your station. Again, right out of the questions. And that one's out of order. That is a ferrite choke. And we're going to talk about ferrite chokes here in a second. So if you get a report from your neighbor that you're interfering with their equipment, if they complain, investigate. That's the first step you need to take. You check your station that it's operating properly and with good amateur design. Easy way to check is check with your TV or radio. If you turn it to the same channel and you get the same interference when you're transmitting, well, there you go. You're the cause of it. If not, there may be something else going on. Things have shifted a lot. Cable and satellite TV connections have been generally less susceptible to a TVI than over-the-air TV reception. But when it does happen in a non-fiber distribution system, when it actually uses RF, you may find that the problems are caused more frequently by a loose or corroded connector. So make sure that all TV coaxial connectors are properly installed. They are these funny little ones that look like this, and if they're not properly installed, may be a source of interference. What happens if you receive interference from your neighbor? Well, it's most likely coming from a Part 15 device. These devices are everywhere. They're unlicensed devices that generate low-level RF signals. They can be anything. They can be a cordless phone system, a baby monitor, switching power supplies. All of those are Part 15 devices that generate signals that potentially interfere with you. And if you determine the interference is indeed coming from your neighbor, what do? Well, again, you check your station, you work with your neighbor to try to identify the source. And if it comes down to it, you have to politely inform them that FCC rules prohibit unlicensed devices from interfering with a licensed service. You as a ham operator are a licensed operator, your station is licensed, and legally you don't have to put up with interference from unlicensed devices. Okay, we're just about to the end here. What can cause radio frequency interference? Fundamental overload, harmonics, spurious emissions. Yep, any one of those things can do it, so all of the above are correct. Which of the following actions should you take if a neighbor tells you that your station's transmissions are interfering with their radio or TV reception? Make sure your station's functioning properly. Immediately turn off your transmitter and contact the nearest FCC office for assistance. I don't think that's going anywhere. So all of these choices aren't correct. We don't know what a harmonic doubler is. So correct answer, make sure your station is functioning properly, does not cause interference to your own radio or television tuned to the same channel. What should be the first step to resolve non-fiber optic cable TV interference caused by your amateur radio transmission? Again, non-fiber optic uses radio RF signals, and quite often the problem will be in the TV feed line coaxial connectors. Make sure they are installed properly. And you're operating on a repeater, and the person you're talking to, you receive a report from them that your audio signal through an FM repeater is distorted or unintelligible. Many things can cause that, all of these choices. It could be your transmitter slightly off frequency, your batteries are running low, or you're simply in a bad location. What could cause a broadcast AM or FM radio to receive an amateur transmission unintentionally? Well, that's because that poor little receiver is unable to reject strong signals from outside the AM or FM band. And what should you do if something in a neighbor's house is causing harmful interference? You want to do all these. Work with your neighbor to help identify it. Make sure your neighbor is aware that rules prohibit interference with a licensed service, and check your station to make sure that it meets the standards of good amateur practice. What can you do if you're told your FM handheld or mobile transceiver is over deviating? That means that you're driving it too hard. Just talk further away from the microphone. That'll cut back on the deviation.
With the APRS GIS data, GPS data, and the mapping, what sort of a format is that? Are we talking about an image with a map, or how is that different than, say, coordinates or something like that?
Okay, great question. If you go to this website, aprs.fi, you'll actually see a map of APRS data that's being transmitted worldwide. APRS-FI will probably initially start up in Finland. That's where it's located. But you can tell it, you can put in call signs, it will search for those call signs, and you can get a map of Mendocino County that shows our APRS node, which is on Laughlin Peak, and any of the stations that are connected to it. So you may see somebody driving in their car transmitting APRS data. There might be somebody on foot or on a bike. All of those can be transmitted and viewed, in this case, on aprs.fi. Pretty neat. It also has the weather information too. You'll see stations that are transmitting. It'll say a call sign with WX after it for weather, and you can get weather data there as well.
Okay, thanks. I'll check that out. I appreciate that.
Yeah, take a look at that. It's pretty neat. This is what I wanted to share. The question was about APRS and what does it show. This is a map of the APRS node that's right up here on Laughlin. You'll notice here there's one that says WX, that's weather. Here's Nick's call, KI6RIT-B. Nick was on a bicycle running APRS, and you could see his path there. Over here, you can search for call signs. Oh, is that what that? Oh, that. Okay, I see the D. Okay, sorry about that. Okay, but this is what an APRS map looks like. If you're tracking somebody and they've been through there, you can actually see the path that they've taken, the route that they've been on. So, real quick, that's APRS. That's what an APRS map looks like, and some of the data that you can get off of it.
Quick question. I was looking at the pattern of that J-pole antenna transmission signal, and I was noticing that big cleft. Is that, if you orient that J-pole around that vertical axis, does that cleft in transmission, I mean, is that pretty consistent and predictable? Like, could that negatively affect your transmission if that, depending upon where your J-pole is twisted or rotated?
Can I try that one, Tim?
Sure, go ahead.
I've seen some studies about J-poles, and they are very sensitive to their surroundings, and they're very sensitive to whether or not you isolate the antenna from the feed line. And we haven't talked about that, but balunds are often used and HF frequencies to isolate the antenna from the feed line so that you don't get that standing wave ratio coming back down the feed line, because not only does that impact the radio transmitter itself, but it also radiates. And so it distorts the signal pattern of your antenna. I always thought these were pretty omnidirectional, but there's a ham in Anderson Valley that has one of these on top of his tower, and he has to turn it to the direction he wants to talk, or he can't get a signal out of it. So you can't think of these antennas in isolation, because there's stuff around them, you know, your house or your gutters or that pole that this example antenna was on here. Oh, I can't show it to you again, but it doesn't matter. So there are ways to make it function better, but yes, I think there is a directionality to it that most people don't realize, and it's something to play with.